Okay, so we're going to do a couple of examples of finding relative maximums and minimums using our new second derivative test. And let's just sort of write down what that is real quick. So we've got it handy. So let's f is, we said, was twice differentiable. X equals c, a critical value of f prime. Then if f double prime of c is greater than 0, then f of c is a local minimum. If f double prime of c is less than 0, then f of c is a local maximum. And f double prime of c equals 0, f of c, we don't know. And we did a couple of examples last time, or at least sort of talked through a few cases for this third situation that we really just don't know what's going to happen there. It isn't the way with the first derivative test, when the sign of the derivative doesn't change, we know that this is neither a maximum nor a minimum. We had examples where the second derivative was 0, but we had a relative maximum, an example where the second derivative was 0, but we still had a relative minimum, and an example where the second derivative was 0, where we had neither of those. Again, we really have no way of knowing, using the second derivative test, what's going on with the original function. Hopefully, we're going to stay in these first two cases and see what happens. So, we want to find for f of x equals x over x squared plus 1, we want to find any local maximums or minimums. Those can happen only at critical values of f prime. So first thing, always take the derivative. We'll need a quotient rule. That's u prime v minus v prime u over v squared, where u is our numerator, is x, v, our denominator, is x squared plus 1, and so u prime is 1 and v prime is 2x. Throw all four of those at our formula, and we get u prime is 1 times v, x squared plus 1, minus v prime is 2x times u is also x, and we're going to divide all of that by x squared plus 1 squared. We'll simplify, distribute, and we get x squared plus 1 minus 2x squared over x plus 1 squared plus 1 squared. X squared minus 2x squared are like terms. And that leaves us with 1 minus x squared over x squared plus 1 squared again. How do we find the critical values? Those are either undefined values or solutions to f prime of x equals 0. For the undefined values, we're typically looking at maybe a denominator that's equal to 0. But our denominator, x squared plus 1, is not going to be 0 for any real values. If we move that 1 to the other side, we get x squared equals -1. When we take the square root of both sides, we're going to get a complex value. We might also say that no matter what x is, if I square it, I get a positive number. If I add 1 to that, I get an even more positive number. And if I add 2, and if I square that, I get something that maybe is even more positive. And so we can't possibly get a 0 in the denominator. So our undefined values, as in a lot of our examples, we just don't have any of those. And so we'll move on to solutions to f prime of x equals 0. So 1 minus x squared over 1 plus x squared squared equals 0. We'll multiply both sides by 1 plus x squared squared. To cancel that, that leaves us with 1 minus x squared on the left, and 0 times the red stuff is still 0, and that's baby stuff. We get that x is either positive or -1. So f can have an extreme value at x equals 1 or x equals -1, but we have to classify those. That is, we need to tell whether, this could look a little bit more like a -1. We have to tell whether x equals 1 maximizes or minimizes our function. We need to figure out if x equals -1 maximizes or minimizes our function. So we can't just say, our extreme values can occur here, but we need to figure out what kind of extreme values we're dealing with. We'll use our new second derivative test. We're going to plug x equals plus or -1 into f double prime. And if we're going to do that, we better find f double prime. F prime of x is 1 minus x squared over 1 plus x squared squared again. So f double prime of x, again, is a quotient rule with u equals 1 minus x squared and v as 1 plus x squared squared. U prime is easy. V prime, we'll use the generalized power rule. We'll bring down our exponent, subtract 1 to get the new exponent, and then multiply by the derivative of 1 plus x squared. 2 times 1 plus x squared times its derivative is 2x. Start putting all that together into our quotient rule. F double prime of x is u prime v minus v prime u, negative 2x, times 1 plus x squared squared, minus v prime is 4x times 1 plus x squared, and we're going to multiply that by u, 1 minus x squared. All of that stuff is going to be divided by 1 plus x squared, now to the 4th power. We had it squared. We need to square again for the quotient rule, and if you square a square, you're going to get that 4th power. Notice that this 1 plus x squared factor shows up in both groups in the numerator. We're going to factor that out, and we'll be left with negative 2x times 1 plus x squared minus 4x times 1 minus x squared, and all that divided by 1 plus x squared to the 4th. We can reduce that to a 3rd power, distribute, and we get negative 2x minus 2x cubed minus 4x plus 4x cubed all over 1 plus x squared cubed. And in our like terms, we get 2x cubed, let's see, minus, looks like 6x, all over 1 plus x squared, all of that cubed. All right, so our second derivative, I know in a lot of the examples that we do in class, and certainly the types of problems that we usually end up working on, say, quizzes or tests, I encourage you guys to stop simplifying the quotient rule when you get to this point. Skynet always wants you to simplify that stuff, and so you've got some experience doing that. But since we want to actually use that second derivative, we're going to go ahead and make sure that we do that simplification. So all of that is so that we can plug our two critical values into our second derivative. And interpret what we get using the second derivative test. F double prime of 1 is 2 times 1 cubed minus 6 times 1, all divided by 1 plus 1 squared cubed. That's 2 minus 6 over 8. That's negative 4 over 8. That's negative a half. That's less than 0. And go back to our description of the second derivative test. Anytime that second derivative is negative at the critical value that we found, we have found a local maximum. Since x equals 1 is a critical value of f prime, and f double prime of 1 is less than 0, our second derivative test says that f of 1 is a local maximum. There are a lot of things going on here with the second derivative test and a lot of conditions that have to be met. We have a critical value of the first derivative and the second derivative is negative at that critical value. That gives us a local maximum. Just having the second derivative negative is not enough. We have to have a critical value of the first derivative in order to use this test. But the whole point is finding these critical values of the first derivative. So it's not like we're going to evaluate f double prime just for any old values of x. We're always going to evaluate for these special values. What is that maximum value? F of 1 is 1 over 1 plus 1 squared. Remember that was x over 1 plus x squared. Or what? 1/2. For x equals negative 1, what's our situation? Well, we get f double prime of negative 1 is 2 times negative 1 cubed minus 6 times negative 1 all over 1 plus negative 1 squared cubed. Negative 1 cubed is negative 1 again, times 2 makes negative 2. Minus 6 times minus 1 makes positive 6. Negative 1 squared is 1. If we add 1 to that, we get 2. And if we cube that, we get 8. This time, negative 2 plus 6 is positive 4 over 8. And that's greater than 0. And then how do we interpret that? Since x equals negative 1 is a critical value of f prime, and again, f double prime of negative 1 is positive, our second derivative test says that f of negative 1 is a local minimum. that minimum value is negative 1 over 1 plus negative 1 squared is negative 1 over 2 is negative a half. We are bringing all of these functions together to get information about what the graph looks like, what these extreme values are. Each function tells us something different. F, the original function, tells us how far up and down, tells us how high that local max is, how low that local minimum is. F prime tells us where those local maximums and minimums can occur. And F double prime tells us whether we have a local maximum or a local minimum. So all three of these functions tell us different pieces of information, and we need all three of them to get a complete picture of what this function is doing. Just for a little bit of reference, the graph for this and you can graph this on your calculator or using Desmos or something like that, is going to look something like that. We have at the point 1 comma 1/2 a local max, and at the point negative 1 negative 1/2 a local minimum. Graph looks something like that. All right. So that was one example of using the second derivative test to help classify local maximums and minimums. We'll take another example real quick and look at, say, f of x is equal to x to the fourth minus 2x cubed. And we want to find any local maximums or minimums that exist. Let me see. Let me change this up just a little bit. Let's make this 3/2 x to the fourth. I think that's going to make some of our numbers work out a little bit nicer for us. All right. So where can local maximums or minimums occur? Only at critical values of f prime. So f prime of x, this is baby stuff. We get what? 12x cubed over 2 minus 6x squared, which simplifies to 6x cubed minus 6x squared. There are no undefined values for a function like that. It's a polynomial. It's one of the nicest kinds of functions that we have. And so we're going to just jump straight into setting that guy equal to 0. There's a common factor of 6 that we can get rid of. That leaves us with x cubed minus x squared equals 0. We can factor out a common factor of x squared. And when we set those factors equal to 0, we get that x is 0 or x is 1. I do want you to be careful back here at the first step and then maybe in this step that you do not divide out that x squared. While it does occur in both of these terms, doing so loses this critical value. So that would lose that critical value of x equals 0. We just want to be careful that we're being honest with the way that we solve equations. Now, do these critical values maximize, minimize, or I don't know, neitherize our function f. And so the second derivative test is going to help us out here. We're going to plug our critical values into f double prime. F prime, 6x cubed minus 6x squared. We find the second derivative, again, as baby stuff, as 18x squared minus 12x. For x equals 1, we have f double prime of 1 as 18 times 1 squared minus 12 times 1 is 6. That is positive 6. And since x equals 1 is a critical value of f prime, and f double prime of 1 is positive, our second derivative test says that f of 1 is a local minimum. I want the colors here because I want to emphasize again over and over that we are using 3 different functions to get different pieces of information. I need to start with critical values of f prime. I need to plug those into f double prime and look at the sign and then interpret what that means for f, the original function. We're bringing all 3 of these together. Our minimum value, of course, is f of 1 is 3 halves times 1 to the 4th minus 2 times 1 cubed is 3 halves minus 2 is negative a half. So how low does the function go? How low is this minimum? It goes negative a half on the y-axis. What about x equals 0? Well, we'll plug that critical value into f double prime and get 18 times 0 squared minus 12 times 0 is 0. And, well, what happens with that with our second derivative test? Our test fails. So this is a case where the second derivative test is not applicable. We might have a max at 0, might have a minimum at 0, or we might have neither, but this test is not going to tell us that. We have to use that first derivative test. And so let's look at a little section of the number line. I only need to know how the sign changes at 0, and so I'm going to pick a test value, maybe negative 1 and positive a half. I don't need to pick one over here because I already know what happens at x equals 1. We have that local minimum. And in fact, it's even better than that because if we have a local minimum here at 1, we know that the derivative had to change sign from negative to positive there. And we can fill in some of that information already. And in fact, we don't need to test what happens at x equals a half. F prime of negative 1 is 6 times negative 1 cubed minus 6 times negative 1 squared. That's negative 6 minus 6 is negative 12. That's a negative number. Does the sign of f prime actually change? It doesn't. And so we get neither a max nor a minimum value at 0. Now we can go through and do the entire first derivative test, filling in the fact that we knew that the derivative had to be negative and then positive because of what happened at 1. We could kind of shortcut through some of that and take a little bit of advantage of the knowledge that we already have regarding our little local minimum. But the alternative, just do the entire first derivative test and figure out what's going on here at 0. In fact, the graph of this is going to look something like, it's going to sort of fall the way that a parabola might. It's going to flatten out here at 0. It's going to fall a little bit more because our first derivative is negative, stays negative, but then changes to positive. We get that minimum at 1 comma negative a half. Our function looks a little something like that. And again, you can check that out using whatever your favorite little graphing calculator program is. Mine, of course, is this Desmos that I've used several times. And you're welcome to use that. It's nice and free. So, all right. So an example where the second derivative happened to fail on us. Hopefully that doesn't happen too often. In some ways, we sort of got lucky that not only was 0 a critical value of the first derivative, but it was also a critical value of the second. But we most of the applications that we're going to run into when we get into optimization, that type of behavior is not going to happen very often. And in fact, I chose this one specifically because I knew it was going to happen. But that's just kind of keeping us on our toes, not leaning too hard on some of these tools, but knowing that there are limitations to them is very important. So let's take one more. Let's let f of x be cosine squared x minus 2 sine of x. So a trig example. And we're going to restrict x to be just in between 0 and 2 pi. So this is going to cover one whole period of this function. Now we can find the absolute maximums and minimums. We have a closed and bounded interval, and so we're guaranteed to have absolute maximums and minimums. But just because we've found absolute maximums and minimums, that does not necessarily mean that we have all of the relative maximums and minimums as well. There may be other points that at least locally maximize or minimize the function, even though those are not the absolute maximums and minimums. We want to find all extreme values, not just those absolute max and min that we're guaranteed. Start with that first derivative. We need to find its critical values. So what do we have? The derivative of, find the critical values of f prime means we got to find f prime first. F prime of x. The generalized power rule says I can bring that exponent out front to get 2 cosine of x, as long as I multiply that by the derivative of cosine of x is negative sine x. And we're going to subtract 2 times the derivative of sine x, which is cosine of x. And if we simplify that, we can factor out a negative 2 and a cosine of x, and we would be left with sine of x plus 1. Now, just in terms of factoring and simplifying this, I mean, we could just call this negative 2 cosine x sine x minus 2 cosine of x, but our next step, of course, is going to be to set that equal to 0, and having this factored is going to make that a little bit easier. So set our factors equal to 0. Cosine of x is 0 if x is plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, all of those odd pi's over 2. And the only ones in our interval from 0 to 2 pi are pi over 2 and 3 pi over 2. So we can throw away some of these just by virtue of the fact that we have this nice little closed and bounded interval. Let's move this over here. Move the 1 to the other side, and we get that sine of x is negative 1, which tells us, if we look at our unit circle, that x is 3 pi over 2, let's see, 7 pi over 2, negative pi over 2, basically 3 pi over 2 plus 2k pi, where k is some integer. Again, which of those values actually lies in our interval? Only the 3 pi over 2 does. Our critical values are pi over 2 and 3 pi over 2. We don't need any of those others because we're restricting the domain of this function. The second derivative test says I want to take those, plug them into f double prime. So we've got to find that second derivative. If f prime of x is negative 2 cosine x times sine x plus 1, we'll use the product rule, where u is that negative 2 cosine of x and v is sine of x plus 1. Then u prime is 2 sine x and v prime is cosine of x, and u prime v plus v prime u is 2 sine x times sine x plus 1 plus, let's see, u is negative 2 cosine of x times cosine of x again, simplifies to 2 sine squared x plus 2 sine x minus 2 cosine squared x. And if we look at these sine squared x minus cosine squared x, I believe that is some sort of trig identity. Let me look at the back of the book here. I see that cosine squared x minus sine squared x, it's close to what we have. We've got a factor of 2, and we've got a minus sign, is cosine of 2x. And we can replace that sine squared x minus cosine squared x with negative 2 cosine of 2x. Okay. Do you have to go through that pink stuff? No. But it will make evaluating the second derivative just a little bit easier to do. Now we go back and start plugging in our critical values. f double prime of pi over 2 is negative 2 cosine of 2 times pi over 2 plus 2 sine of pi over 2. That's negative 2 cosine of pi plus sine of pi over 2. Cosine of pi is negative 1 times negative 2 makes positive 2. And then sine of pi over 2, of course, is 1, adds up to 3. That's positive. And then our conclusion. Since x equals pi over 2 is a critical value of f prime, and f double prime of pi over 2 is positive, f of pi over 2. Again, 1, 2, 3 functions all coming together to give us what we're looking for is a local minimum of f. And our minimum value, f of pi over 2 is cosine squared of pi over 2 minus 2 sine of pi over 2. Well, cosine of pi over 2 is 0. We square that, we get 0. Sine of pi over 2 is still 1, so this makes negative 2. We're going to do the same for our other critical value, that 3 pi over 2. Plug that into our second derivative. We get negative 2 cosine of 3 pi over 2 times 2 plus 2 times the sine of 3 pi over 2. Cosine of 3 pi is negative 1 times negative 2 makes positive 2. Sine of 3 pi over 2 is negative 1 times 2, and this should be plus, makes negative 2. Add all that up, and we get 0. And our test has failed us again. And so we're going to go back to that first derivative test here at x equals 3 pi over 2. Let's draw our little number line. This guy is nice and closed off at 0 and 2 pi. We have a critical value at pi over 2, and we know that that represents a minimum of our function, and so we're going to say that f prime is negative and then positive. And again, how do I know that? Because I know that I have a local minimum there. And whether we use the first derivative test or the second derivative test, this still has to happen. Just because we got this information from another function doesn't mean it's not still true. And then at 3 pi over 2, we're going to have to look for maybe how that sign changes. So pick a critical value over here, or a test value. Something between 3 pi over 2 and 2 pi would be something like 7 pi over 4. If you turn all of that into, say, pi over 4s, this would be 6 pi over 4, that would be 8 pi over 4, and of course 7 pi over 4 is right in between. F prime, now we need the sign of that, the SIGN, and so now we're not evaluating f double prime. We've got to go back to f prime to do that first derivative test. F prime of 7 pi over 4 is, what was f prime? Negative 2 cosine of 7 pi over 4 times the sine of 7 pi over 4 plus 1. That's negative 2 cosine of 7 pi over 4 is the square root of 2 over 2. The sine of 7 pi over 4 is negative square root of 2 over 2. And we're going to add 1 to that. That is a negative number, negative 2, times a positive number. And square root of 2 over 2 is about 0.7. And if we add 1 to that, of course, we're going to get a positive value. And so negative times positive is a negative number. I don't care what that negative number is. I just need to know that it is negative. And in our number line chart, we know that the derivative is going to change sign at x equals 3 pi over 2, this time from positive to negative, and our first derivative test tells us that we have a local maximum at x equals 3 pi over 2. Our maximum value is f of 3 pi over 2. That is cosine of 3 pi over 2 squared minus 2 sine of 3 pi over 2. Cosine of 3 pi over 2 is 0. If we square it, we still get 0. Sine of 3 pi over 2 is negative 1. Negative 2 times negative 1 is positive 2. Ooh, there we go. Notice in the previous problem where we were looking at this polynomial, that second derivative test was inconclusive, and we had neither a maximum nor a minimum there at 3 pi over, where was it? Where's that problem? Here we go. At 0, our second derivative test failed, and we had neither a maximum nor a minimum. In this problem, our second derivative test failed, but we ended up with a maximum at that critical value. So again, we cannot just look at that second derivative as 0 and say, well, the test fails, we don't know what happens, or the test fails, we get neither a maximum nor a minimum. The choices are not max, min, neither when we use the second derivative tests. The choices are max, min, don't know. And we've got to go back to the first derivative test to be certain. Be a little bit careful. But always, we have those three functions telling us different information. F, how high or low is that maximum or minimum value? F prime, where does that maximum or minimum occur? And F double prime tells us is that critical value from F prime, is that going to give us a maximum or a minimum? F tells us how high or low the function is going to be on the graph. The derivative tells us where those maximum and minimum values can occur, and then F double prime tells us if we have a maximum or if we have a minimum. It sorts them out for us. Again, hopefully in the cases where the second derivative test actually works. From here, we're going to move into optimization, and that's going to be putting these first and second derivative tests to work for us to help us solve some real-world types of applications. The first one that we're going to do is going to be a revisiting of our apartment problem that we did way back at the very beginning of the semester, and we'll see how we can use the ideas that we've been developing over the last couple of lectures to say maximize the revenue from our apartment complex. And then we'll look at some other types of examples that are maybe a little bit more complicated, things where we have a little bit more work that we're going to have to do in terms of the setup. But these are some of my favorite problems that we do this semester. This is one of the fun applications for this first semester calculus. So keep on watching, and thank you.